Today we're going to talk about quadratic equations, which are sort of one level up in complexity from linear equations, and they give a much richer framework to work with. In fact, quadratic equations show up almost everywhere in science and physics and business and mathematics. Quadratic equations are really key to a lot of what we do and why we care about algebra at all. So let's start with a definition. A quadratic equation is an equation which can be written in the form ax squared plus bx plus c equals 0, where a, b, and c are real numbers, and x is a variable. So a quadratic equation is one where one side of it is a degree 2 polynomial. Now, when we say here an equation which can be written in this form, we mean after gathering all the terms on one side. So if you've got an equation which has a degree 2 polynomial on one side and a degree 1 or 2 polynomial on the other, that's going to be a quadratic equation also, as long as you bring it to the other side. That is, as long as this leading coefficient a is not 0. If a were equal to 0, then this would just be a linear equation, and we've already looked at how to handle those. Quadratic equations are ones of this form, where we've got an x squared term and maybe an x term, maybe a constant term, but no higher power terms. This form right here is called standard form. And we'll often talk about putting an equation, a quadratic equation, into standard form, which means writing it down just this way. We're going to want to do that often because the techniques that we have for working with quadratic equations are a little bit more complex than what we had for linear ones, so we want to make sure that we're all starting from the same point. Now, the difficulty in solving quadratic equations is that you can't usually get x by itself. When we were working with linear equations and trying to solve those, our strategy was to get the variable by itself entirely. Get it on one side, get everything else on the other, divide out what we needed to so that we could isolate the one variable by itself. We can't usually do that with quadratic equations. Usually, we've got two different terms involving x here, and they aren't like terms, which means they don't combine together, and so we need a new way of approaching this. We're going to have a couple of ways of doing that. But they are, at the end of the day, based on the same idea. And there's one underlying idea that really makes solving quadratic equations possible. If we didn't have this, we really couldn't get anywhere. And it's called the Zero-Factor Theorem. Zero-Factor Theorem makes a statement that when I say it will likely seem very intuitive to you. It won't seem like I'm saying very much, but it turns out that what this statement of this theorem is very powerful. It says that if a and b are real numbers and a times b equals 0, then a equals 0 or b equals 0. So if I've got two numbers and they multiply together and they equal 0, then that means that one of the two factors that I had to begin with had to be 0 in the first place. This isn't too difficult to convince yourself of. If you imagine that neither one of them was 0, If we suppose that a and b are both non-zero, well then each of them are either positive or negative. If they were both positive, then a times b is the product of two positive numbers, which is positive, not zero. If they were both negative, then their product would be positive, not zero. And if one was positive and one was negative, their product would be negative, but again, not zero. The only way for two real numbers to multiply together to equal zero is if one of them was zero to begin with. Now, this is something that we're very familiar with, but it's also absolutely essential to this whole process. And this is the key that we're going to use. We're going to use the Zero-Factor Theorem and factoring to solve some quadratic equations. So let's see how this goes. I really want to emphasize that we're using the zero-factor theorem here because when we understand why what we're doing works, it helps us to avoid errors and to adjust to new situations that we run into. So let's take an example. Let's suppose that we want to solve the equation x squared minus 6x plus 8 equals 0. We want to find all the values of x that will make this equation true when we plug it in. Well, one thing that we can try to do is to factor. We can try to factor the quadratic polynomial that's on one side of the equation and use the zero-factor theorem. Now, in this case, we can factor this polynomial the following way. We can look at our coefficients and see here that x squared has a coefficient of 1. Therefore, we can try factoring like this, and we're looking for two numbers that multiply to equal 8 and add to equal -6. Well, if you try a few things, we can start going up the factors of 8 and say, well, we get 1 times 8 is 8, but does 1 plus 8 equal -6? No. We can try a few things, and we can realize that -2 and -4 do this. So -2 plus -4 is -6, and -2 times -4 is +8. And so we've rewritten the left-hand side of our equation in the form x minus 2 times x minus 4 equals 0. Well, let's see why that helps. We've now written this left-hand side as one number, or one expression, times another expression equals 0. By the zero-factor theorem, this equation is only true if one of the two factors on the left is 0. In order for x minus 2 times x minus 4 to be 0, one of those must have been 0 to begin with. So that's what we can go to next. We can say, therefore, x minus 2 equals 0, or x minus 4 equals 0. And this is where the power of the zero-factor theorem, combined with factoring, helps us out. We started with a single equation that had a degree 2 polynomial in it, a quadratic polynomial. Now, then we factored, and we used the zero-factor theorem to split things up. Now, instead of having one equation with a degree 2 polynomial in it, we have two equations, each with a degree 1 polynomial in it. we've taken our complicated problem and turned it into two smaller, less complicated problems that we know how to deal with. A lot of algebra is taking a complicated problem and turning it into one or more smaller problems that we already know how to deal with. Now this we can work out. We can work out each one of these equations, these green equations, individually. And so we can add 2 to both sides of the left and get x is equal to 2, and add 4 to the right and get x is equal to 4. And so what we have here are 2 different values of x that, according to our computations, will make the original equation true. So our solution set for this equation is 2, 4. So we can look at a few things. First of all, assuming we've done everything correctly so far, we see that we actually have 2 solutions to this equation, which is not something we saw when we were looking at linear equations. Linear equations only had 1 solution, or sometimes no solutions. We didn't have any situations where we had 2 different solutions, but this is very, very common when we work with quadratic equations. In fact, quadratic equations usually have 2 different solutions. Now let's go and check this. Let's check our work. As we start working on more complicated problems, it's going to be good for us to make sure and check our work more regularly. So let's check the potential solution x equals 2. We want to go back and plug that into the original equation. We get 2 squared minus 6 times 2 plus 8. Let's simplify that down. That gives us 4 minus 12 plus 8. And 4 minus 12 is negative 8. Negative 8 plus 8 does in fact equal 0. So that checks out. If we plug 2 into the original equation, we do in fact get a true statement. And if we plug in x equals 4, we get 4 squared minus 6 times 4 plus 8 equals 16 minus 24 plus 8. Now 16 minus 24 is negative 8, plus another 8 is 0, and that checks out as well. So we see that looks like we did it right. There are in fact 2 solutions to this problem, 2 and 4, and we found that by factoring the polynomial on the left and using the Zero-Factor Theorem. Let's look at another example. Let's look at the equation 2x times x minus 2 is equal to 6 plus 3x minus x squared. Now, when you're working with quadratic polynomials, you want to always get 0 on one side of the equation. You're going to want to move everything over to one side of the equation and leave just a 0 behind. And the reason for that is that the Zero-Factor Theorem only works with 0. If I know that 2 numbers multiplied together equals 0, I know that one of them has to be 0. But that's not true of any other number. If I know that a times b equals 5, well, I don't know anything about a and b. Well, I know they're not 0, but that's literally the only thing that I know. So in order for us to use the Zero-Factor Theorem, we need to have 2 things multiplying together to equal 0. And so that's why we need to get 0 on one side of the equation. So let's go ahead and do that. Now, the first thing that you do want to do is to expand both sides of the equation. So in this case, I'll write 2x squared minus 4x, and that'll be 6 plus 3x minus x squared. And I want to gather all of my terms on one side of the equation. Now, it doesn't matter whether I gather everything on the left or on the right. The one thing that I will say is that it's usually easier to put yourself in a situation where the coefficient of x squared is positive. So in this case, I'm going to bring my x squared terms over to the left. And therefore, I want to bring everything else over to the left as well. So I'm subtracting 6 from both sides. I'm subtracting 3x from both sides, and I'm adding x squared to both sides. I'm doing all of these at once because we're pretty familiar with it now. So 2x squared plus x squared is 3x squared. Negative 4x minus 3x is minus 7x. And then we have a negative 6. And then we just have 0 on the right. So now we're again in a situation where if we can factor the left-hand side, we can get a case where we can use the zero-factor theorem. So we want to figure out how we can do this. So we want to factor the polynomial on the left. The polynomial on the left has a coefficient other than 1 in the first slot as the coefficient of x squared. So I'm going to factor by grouping. And so we need to take the first times the last term and get negative 18, because that's 3 times negative 6. And then we want to find two numbers that multiply to equal negative 18 and add to equal negative 7. Well, I like just going up the factors of negative 18. So 1 times negative 18, and I asked, do those add up to negative 7? They don't. And then 2 times negative 9, do those add up to negative 7? Oh, they do. Okay, great. So now I can rewrite the polynomial over here as 3x squared minus 2x minus or plus 2x rather, minus 9x minus 6 equals 0, and do my factoring by grouping thing. So we'll factor the greatest common factor out of 3x squared plus 2x. That'll be x, and we'll be left with 3x plus 2. Factor the greatest common factor out of negative 9x minus 6. That'll be a negative 3, making sure to factor out the negative so that the leading term becomes positive. And now we have 3x plus 2 as a common factor in both remaining terms. And so this whole polynomial factors as 3x plus 2 times x minus 3. And so, having gone through the factoring process, we have again turned our equation into one where we have two factors multiplying together to equal 0. And we can use the zero-factor theorem again. So from here we can conclude that either 3x plus 2 equals 0 or x minus 3 equals 0. And again, we can solve each of these separately. So the equation on the right has a solution of x equals 3. We can subtract 2 from both sides here, divide by 3 to get x equals negative 2/3. So here we got our solutions again. We got two solutions. We have that x is equal to negative 2/3 or x equals 3. Or we could write it as the solution set, which is the set containing negative 2/3 and 3. We can use the zero-factor theorem a lot of ways, and as long as we keep that in mind, remember how we're working with it, we can handle a lot of things even if they look a little bit different than what we've seen so far. So let's take another example. Let's look at 4x squared plus 6x equals 0. Now this is a quadratic equation because it is a degree 2 polynomial. However, we don't have a constant term here, which makes things a little bit simpler. And in fact, we can handle things in a slightly faster way. Now, factoring is again key. We want to use the zero-factor theorem, which means we need to write one side of this equation as two things multiplying together to equal 0. So here we're going to factor the greatest common factor out of the left-hand side. In this case, we can just do this because we just have the two terms. And if we factor the greatest common factor of 2x out, we get 2x times 2x plus 3 equals 0. Well, now we can use the zero-factor theorem again. Even though it doesn't look exactly like we did the ones that we did before, this is still two things multiplying together that equal 0. Whenever we have two things multiplying together that equal 0, we can always break that up to say that either the first one equals 0 or the second one equals 0. And now we can go and solve each one. So we can divide by 2, get x is equal to 0, or 2x equals negative 3, and get x is equal to negative 3/2. So in this case, we have a solution set, which is 0, negative 3/2. And so you can see that by using the zero-factor theorem cleverly, we can make short work of problems, and sometimes even shorter than the last couple of examples that we had. We can also use our techniques of working with quadratic equations to solve certain rational equations that we couldn't before. So for example, let's look at 1 over x minus 1 plus 3 over x plus 3 equals 1. And let's try to solve this equation, find all the solutions to it. Now, as always, as before, we can't solve for x while it's still in the denominator, so the first thing that we're going to have to do is get it out of the denominator, and as before, we do that by multiplying by the least common denominator. Now in this case, the least common denominator is just the product of the two denominators that we have, because we have no common factors involved, so we'll multiply both sides by this least common denominator. Now, when we multiply by both sides, then we really wind up just multiplying this denominator by every term. So we'll go ahead and jump straight to that step in the process. So we multiply x minus 1 times x plus 3 on both sides of the equation. And then we've got some cancellation to do. X minus 1 cancels with x minus 1 in the first product. X plus 3 cancels with x plus 3 in the second product. And then we can go ahead. So we've got x plus 3 times 1, which is just x plus 3. And then we've got x minus 1 times 3, which we're going to have to distribute through. And then we get x minus 1 times x plus 3 on the right-hand side of the equation. Expanding things out, we get x plus 3 plus 3x minus 3 on the left, x squared plus 3x minus x minus 3 on the right, and simplifying things down further, x plus 3x is 4x on the left, 3 and negative 3 cancel out, and x squared plus 2x minus 3 is what we have on the right. Now, to get 0 on one side, which is still our goal, we need to subtract both sides by 4x. Notice that at this point we've gotten things down to a quadratic equation, and so solving the problem is just a matter of solving the quadratic equation using the same methods that we had before. So we get 0 is equal to x squared minus 2x minus 3. And we're going to use the zero-factor theorem again by factoring the quadratic polynomial on the right. Its leading coefficient is 1, so we can factor this by finding two numbers that multiply to equal -3, add to equal -2, and those two numbers are going to be 3 and 1. So now we've reduced our problem to the point where we have that two expressions, x minus 3 and x plus 1, are multiplying together to give us 0. Well, the only way for that to happen is for one of those two factors to have been 0 to begin with. So this means that 0 is equal to x minus 3, or 0 is equal to x plus 1. We can solve each one of these for x, and we get that x is equal to 3, or x is equal to -1. Now, before we write down the solution set, we need to check each one back in the original equation. So if we check 3, then we get 1 over 3 minus 1 plus 3 over 3 plus 3 equals 1. And we want to know if that's true, so we might put a question mark over the equal sign. And that will simplify to 1/2 plus 3 over 6 is 1/2, and 1/2 plus 1/2 does in fact equal 1, so that checks out. Let's check -1. We'll have 1 over -1 minus 1 plus 3 over -1 plus 3, and does that equal 1? Well, 1 over -1 minus 1 would be 1 over -2, which is 1 over -1/2. And 3 over -1 plus 3 will be 3 over 2, and -1/2 plus 3/2 does in fact equal 1, so -1 is also a solution to this equation. So in fact we get that 3 and -1 are the solutions to this rational equation that we got by applying our techniques with quadratic equations and the zero-factor formula. Let's look at another equation which is simple, simpler than some of the others we've seen. Let's look at the equation x squared minus 10 equals 0. Now there are a couple of ways for us to approach this problem. And one of the ways, the better way to do it, is to continue thinking about things in terms of factoring and the zero-factor theorem. So we're going to apply the zero-factor theorem again. And to do that, we want to factor the left-hand side. And we're going to do that using the difference of squares formula. Now, you might object and say, well, x squared is a perfect square, but 10 isn't. Well, I grant you that 10 is not a square number, but it is the square of some real number. In fact, 10 is equal to the square root of 10 squared, basically by the definition of the square root of 10. So that means that we can write this equation as x squared minus the square root of 10 squared equals 0. And now we can apply our difference of squares factor formula and factor the left-hand side of this equation as x plus the square root of 10 times x minus the square root of 10 equals 0. And once again, the zero-factor theorem tells us that this means that x plus the square root of 10 has to equal 0, or x minus the square root of 10 has to equal 0. Now, each one of these equations we can solve for x in the normal way. The square root of 10 is a funny looking number, but it is just a number, which means that we can add or subtract it to both sides of this equation as we like. So we get x is equal to negative square root of 10, or we can add square root of 10 to both sides on the other equation and get x is equal to the square root of 10. So we have this solution set of the square root of 10 and negative square root of 10. This is sometimes abbreviated as saying x equals plus or minus the square root of 10. However, I want to emphasize that this plus or minus notation here is not actually a mathematical operation. It really is always just a shorthand for either the positive thing or the negative thing. So when we say x is equal to plus or minus negative 10, that really is just a shorthand for what we wrote up above. X is equal to negative 10, or x is equal to negative square root of 10, I should say, or x is equal to the square root of 10. Now, if we did this process with an arbitrary number in place of the 10, then we would get the following result, which we will use reasonably often. We call the square root property, which says that if x squared minus c equals 0, or equivalently, if we have x squared equals c, notice that those are two equivalent equations. We can get from one to the other by adding or subtracting c to both sides. Then this means that x is equal to square root of c, or x is equal to negative square root of c. We'll use this reasonably often. In particular, we're going to use this in the next talk where we develop a formula to help us solve quadratic equations that we can't do using factoring.